Some people have gone and looked at it, but some people haven't, so let's kind of evaluate what's going on with it. Rule 1 was larger conjugate bases meant that they were more acidic. And I said that that was the same thing as Rule 3, which is talking about resonance. And that's where things can get a little bit odd, because if we went through and looked at, say, HBr, which we know to be a strong acid, we have Br minus. So this is something that a lot of people were going through and doing, saying, well, but Br minus doesn't have resonance, so that means it can't be a strong acid. No, that just means we used a rule earlier on in our sequence. Right? What we're talking about is if we have resonance, that species becomes a stronger acid, potentially, than a species without that resonance. Right? And so we have to make sure that we're making fair comparisons. So comparing HBr to a carboxylic acid is not a fair comparison. Right? I want to compare that carboxylic acid to, say, an alcohol. And I don't really care what those carbons are necessarily. Why is the one on the left more acidic than the one on the right? Right, well, if we go through and follow the rules as we've got them written down, conjugate bases. So we're evaluating our conjugate bases. We'd remove the hydrogen in both cases. We'd have a negative charge on the oxygen, and we'd have a negative charge on that oxygen. Okay? Well, there's no size difference. The atom that's holding the charge is the same. So there is no size difference. How about electronegativity? Well, again, what's the atom holding the charge? It's oxygen and oxygen. There's no difference in electronegativity. Okay? Rule 3 and Rule 4, the old ones, were what Gen Chem threw at you, and we could start to apply those. As we add more oxygens, it becomes more acidic. Okay? Well, there's more oxygens in a carboxylic acid, so it becomes more acidic. Okay? But what happens with Rule 3? We're saying stronger acids have conjugate bases with resonance. If we go through and look at the carboxylic acid, what does it have? It has the opportunity for resonance. I've taken that negative charge and I've placed it on a different oxygen atom. The alcohol doesn't have that ability. Okay? So that explains the increased stability of the carboxylic acid, okay, or the conjugate base of the carboxylic acid, which means it's more acidic. Okay? So hopefully that makes sense as a resonance rule. Why is that the same thing as rule number 1? Well, rule number 1 is just talking about the size of the atom holding the charge. The bigger the atom, the more stable it becomes. Well, why is resonance a bigger atom? What's that? The atom isn't bigger, but the charge is being shared across more atoms, meaning the charge can be occupying a larger space. The resonance effect is a size effect, but it's a size effect of where the electrons can exist in the molecule. Rule number 1 is where can the charge exist on an atom. So they're effectively the same thing, they're just being applied to different situations. Why would I look at the atom first? Well, the atom's where the charge is held. It makes sense to look closest to the charge first. When we move to the induction effect, hydrogens that are closer to electronegative elements are more acidic. Okay, well, why is that the same as Rule 2? Well, Rule 2 says stronger acids have higher electronegativity. Why? Higher electronegativity literally means that that atom is pulling electrons away. If I have an electronegative atom somewhere in the molecule, that atom is going to pull electrons into the structure or towards it, all the way through the sigma structure, all the way back to wherever that hydrogen is. Okay? So rule number 4 is really an electronegativity argument again, but now applied to the molecule. So when we're looking at these relationships, we're just saying, well, what's the reactive thing? What directly affects it? The first thing that's going to affect that reactive thing is going to be the atom. Then it's going to be the molecule. And each of those stages, we need to evaluate size and electronegativity. And if we think back to Unit 1, probably lecture number 2, there was a little section where I said the trends that we see in the periodic table. And the trends that I said were important were size and electronegativity. Right? Why did I say it was important then? Because that dictates everything about acids and bases. Right? That's what we're using to predict our acid strength. Right? What you were taught in Gen Chem was ultimately just memorize the result, because we didn't want to explain to you in Gen Chem both the sequence of numbers and calculations and how do pieces fit together to get molecules and structures. So we tried to simplify that system. Right? Arguably, we've oversimplified it because now all you remember out of Gen Chem is calculations. You don't remember any of the chemistry part. Right? That's what happens. Right? Conversely, I'm doing the opposite because I'm doing the complete opposite. I'm now moving all of the equations and just focusing on the chemistry. Right? So I'm just as bad as the Gen Chem. Okay? But we balance. So if we go through and take a look at these, which is the strongest acid? Okay, when we're looking at acid strength, we're concerned about the conjugate base. Okay, so remove the hydrogen and see what you get. So let's start with the top one. I remove the hydrogen from H3O+. What do I get? H2O. I remove the hydrogen from H2O. What do I get? Disagree. It is not OH. Someone said it over here. OH negative. Which of those is more stable? H2O. Right? Not necessarily the nicest thing, but I do reference something called a face test every so often. Okay? What that face test means, I throw either of those in my face, do I complain about one of them more than the other? Okay? The one I complain about, I don't want thrown in my face. That was a bad thing to do. I want to do the other one. Right? So if I go through and look at this, OH minus burns my face. H2O just means I'm cleaner, theoretically. Right? Well, cleaner isn't bad. That means H3O plus is a strong acid because it's producing something that's not bad. H3O plus now in comparison to H2O is a stronger acid than H2O. Why? Look at the conjugate base, the charge. Okay, we're evaluating the stability. There's a charge in hydroxide. That makes it bad. Right? Make sense? HF versus HCl. Same process. Draw the conjugate base. Remove the hydrogen from HF and we get F minus. Hopefully we never see that. That was a great joke. Boom. HCl. Cl minus. All right. So we compare those conjugate bases again. Charge. Well, they both have the same size charge. They're both negative. So charge doesn't help me. So I'll move to the next thing I want to evaluate. Well, what's the next thing I want to evaluate? Well, what's the atom holding the charge? I have fluorine and I have chlorine. Okay? There's two aspects that we can look at, both size and electronegativity. Okay? Believe it or not, they're competing with each other, which means we have to look at one before the other. This is why when you look at the rules, the first thing I gave you as rule number 1 was size, because size is going to be a stronger contributor to deciding your acid strength or stability than electronegativity. Which one of those is more stable? The chloride becomes more stable. Why is the chloride more stable? It's bigger. So we go back to the rule. If bigger said more stable, that means HCl is a stronger acid than HF. Which hopefully everybody got right anyway because you were required to memorize that HCl was a strong acid and HF was not. Okay? So why is bigger now better? Well, again, what's the dangerous thing? What makes both of those structures bad? The charge. What charge? A negative charge. What makes the negative charge? Electrons. So let's draw an electron. Let's try that again. Everybody see the little red dot? That's an electron. Okay? That is fluoride. Okay? There's another electron. That is chloride. Okay. When we touch electrons, it hurts. This is why you're told not to shove forks in electrical outlets, because they're full of electrons. You don't do it. Or stick your mouth on power cords when they're plugged in. That's also a very bad idea. Okay. I didn't think it would work, but it does. Don't do it. You now have a choice. You have to stick your hand in one of those two circles. Which circle do you stick your hand in? You'll probably stick your hand in the bigger one. Why would you stick your hand in the bigger one? If you touch that red spot, you just stuck a fork in the electrical outlet. That hurts. Okay? So we don't do that. You're going to stick your hand in the big one because the odds that you encounter that little red dot are now lower. Okay? What does that mean? The odds that that red dot does anything are now lower, which means it doesn't react, which means more stable. Cl minus is now the more stable conjugate base. That makes HCl a stronger acid. Okay? So it's not just memorize the rule. What is the reasoning behind that rule? Ready to try another one? H2O versus HF. We're looking at OH minus versus F minus. Which is the stronger acid? Right, well, they're both negatively charged. Is there a size difference? Right? This is important to address because this was a question in exam 1. In fact, it was the very first question in exam 1, and based on the exam rewrites, we're still missing the concept behind that. Right? Here's our electron on hydroxide. Here's our electron on fluoride. Here's the size of oxygen. Here's the size of fluoride. Are they the same? Are they the same? No, the fluoride is a little bit smaller. That's true. Is it relevant to sticking your hand in one of these? No. It's a negligible effect. So when we look across a row, the size does have a small change. That change is so irrelevant that you should not be saying there's a change in size across a row. Okay? The electrons are going into the exact same energy level. For all intents and purposes, the size stays the same. That becomes super important when we evaluate these because we now can't use that rule to distinguish stability between these two. So what would we have to do? The next rule and move to electronegativity. Fluoride is more electronegative than oxygen. What does that mean? It's going to hold on to that electron tighter than the oxygen. Which means if I try and act and say, well, I want to interact with that electron and reach in, fluoride hits me and it's not nice. Oxygen, on the other hand, may not like me, but it at least accepts it. Fluoride is now less or more stable because it doesn't interact. If fluoride's more stable, HF is the stronger acid. Okay? So you can memorize the rule, you just have to make sure you apply that rule. As we continue to move through these, you should see that the patterns continue. Okay? We'll have to draw out H2O. Actually, I'm not drawing it out. We could look at it as negative hydroxide, OH minus. The other one, you should be able to draw out its structure, but it's our carboxylic acid. If we again remove that hydrogen, charge, they're both negative. Size, oxygen and oxygen, there's no difference. Right? Atom effect on electronegativity, there's no difference, it's the same atom. Now I can move to a molecular effect. I move out and look at the rest of the structure. What does the rest of the structure do? Okay, resonance plays a larger role than the inductive effect. Do I have resonance for either one of these? Okay. For those of you that aren't familiar with how to do this, we try. If you don't know, do it. I'm going to take those electrons and I'm going to share them with the hydrogen. What would the result be? I would have exceeded the octet on hydrogen, so I have to break a pi bond. I do that by breaking the only pi bond that would be present, which would be literally the one I just formed. The result being nothing changed, so no resonance. What happens in the other case? I still exceed the octet. And just like we did with every other resonance structure, as soon as we've exceeded the octet, what do I need to do? Break a pi bond. Yes, I can break the pi bond I just made. Is there another choice?
Yes.
Yes. And I will break that pi bond by pushing the electrons away from the issue, away from that exceeded octet. The result being another structure, where the negative charge is now located on a different atom. If I now go to look at the effective negative charge for that molecule, it is 1/2. Why is it 1/2? I mean, each of those is a -1. Why is it a half? Say it again. They're sharing between the two. With resonance, I have to evaluate both. I can't evaluate just one. I have to evaluate both simultaneously. So if I evaluate both simultaneously, the charge on that oxygen, the red one there, is a -1. Plus the charge on that same oxygen in the other structure is 0. That's spread across two structures. The average charge is -1/2. That's where that effective -1/2 charge comes from. Which is more charged, -0.5 or -1? -1 is more charged. Okay, so resonance, again, stabilizes our charge. The more stable the conjugate base, the more acidic our original compound. The last one is an inductive effect. It's the same kind of rules. CH3 minus we end up with H2. What is the difference between these two structures? Hydrogen versus fluorine. Okay. We're not looking at a size effect now. The charge is still a -1. That charge is held on a carbon in both cases. Okay. Carbon is the same atom in both cases, so I move to a molecular effect. Is there resonance? Nope, so I move to an inductive effect. Is there an electronegative difference? Fluoride is more electronegative than hydrogen, which means what is it doing to the electrons between the fluorine and the carbon? It is pulling them inwards, which then means what does the carbon do to that negative charge? It also pulls it inwards. Okay? That's stabilizing the charge. It's pulled it into the structure. In all of these cases, what we were evaluating is the acid strength. We get used to evaluating acid strength. Okay? But you're not always asked to evaluate acid strength. You're also asked to evaluate base strength. And that tends to freak everybody out and go, oh my God, I can't possibly do this anymore. Okay? Because it must be an entirely new set of rules. No. It's the exact same set of rules. You will look at charge, you will look at size, you will look at electronegativity, you'll look at size again, the molecular effect being, what is our size effect? It's in quotes. Resonance. You'll look at a molecular effect of electronegativity, also known as the induction. And then you'll look, if you really have to, at hybridization. Okay? Because what changes is we change the hybridization. I can't say bad words.
That's not a bad word.
Everybody freaks out at that. I can't write bad words because then it's permanently written down. If I can say it, then it doesn't really matter, right? Because no one can catch me on that unless, of course, I was being recorded. What happens with our hybridization? As we increase hybridization, what do? We decreased electronegativity. The hybridization effect is really just an electronegativity effect, an atom effect. Okay? Why is it listed as the very end? Most people won't see the hybridization effect. The hybridization effect on acid-base strength is usually being directly asked upon. Almost all other cases are going to involve the first 5 rules. Right? So we kind of hope that we never have to deal with the hybridization. It usually shows up once, and that's about it. The other ones show up multitudes of times. Okay? Multitudes of times when? Whenever I'm concerned about stability. Because we're looking at reactions, when am I concerned about stability? All the time. Okay? It becomes a mantra. Charge, size, electronegativity, resonance, induction. Okay? It is so important that you will find other instructors come up with mnemonic devices for it. I find the mnemonic devices don't work for me, so I don't memorize them. Okay? But if you look out on the internet, you might hear something about cardio, just in case you were curious. Okay? That's why it says O carb, because I didn't know what the O stood for. It's literally what it is. I could figure out the rest. Okay? So, let's take a look at an example. I meant to actually get it drawn into the structure, or into the PowerPoint, and then ran out of time. For those of you that have started the homework, you might be like, this looks really familiar. Yep. Because a lot of people have been asking questions about it, so let's take a look. Where's the most acidic hydrogen? Too late. You didn't figure it out. Guess what? You should try all of them. If you don't know the answer, which I fully expect you to not know the answer right now, you need to try removing every single hydrogen and evaluating the conjugate base of every single hydrogen. How many hydrogens are in this structure? 6. Does that mean you have to draw 6 different conjugate bases? No. But you just said draw every single one. Every single unique one. But remember how in Unit 2 we went through a spectroscopy and we said that not all hydrogens are unique, that some of them have the same chemical environment? There's a reason we talked about spectroscopy first. Right? We don't have 6 unique hydrogens, we have 3. So what I want to do is think about what happens for those 3 hydrogens. Probably orange was not a good color to pick. So I want to evaluate the stability for each of those 3 products. Conveniently, I drew that way too large for me to go through and do this. So I'm going to give you a second to start working on those. And then I'm going to erase it and redraw it so I can fit all the other ones in.
So, is there supposed to be an arrow there, or is that?
There's no arrows.
Well, no. It looks
Okay.
like an arrow.
I know what it looks like. That's just a hydrogen.
Okay.
Okay? You need 3 different structures. Negative charge accordingly for each of those structures. Start drawing out first that parent structure. Once you've got the parent structure drawn, you can start removing hydrogens and drawing the conjugate base. You need to be drawing 3 structures. If I don't think you're drawing 3 structures, I'll turn it into a quiz that'll give you less than 2 minutes to do. Okay. So we've got our original drawn. I've added curved arrows, okay, to show the removal of that hydrogen. Remember, carbon is more electronegative than hydrogen, so I'm going to remove the electrons and place them on the carbon atom. Okay. We're taking electrons from a bond. I can either go bond to atom. Since I want to go simple first, I'm going to go bond to bond or bond to atom. So I want to go simple first. I want to go just bond to atom. Okay. The result being is that the hydrogen would no longer be attached. So I see H plus floating around in all 3 cases, right? That would be a time to say yes.
Yes.
Okay. Or no if you didn't agree with me. Okay. Are those 3 structures correct?
No.
What's wrong with them? Okay. Remember, I took the electrons in that bond and I placed them on the atom. So minimally, there's a lone pair in each of those cases. So let's show the lone pair. Do you have to show the lone pair? arguably, no, you don't have to, as long as, what have you shown? The charge. Because if you don't specify the lone pair or the charge, then they become implied hydrogens and we don't know. All the way back to Unit 1. Okay? So we've shown the lone pairs there. Now, that's nice. Okay? Except, what else is happening here? Once we've shown our structure, we need to evaluate charge. Every time you draw a structure, think about formal charge. You only need to do your formal charge where you've drawn an arrow. So for the red one, I'm evaluating the formal charge on the hydrogen and that carbon. Nothing else, because nothing else was affected by the red arrow. Make sense? So if I look at the formal charge for that red carbon, 4 valence electrons minus 3 bonds minus 2 unpaired electrons. That's my version of minus. And we would have now minus 1. What happens for the purple one? Same deal. Wherever the lone pair is, we have a minus charge. Okay. As a nice last minute check, what is the overall charge in the purple products? Neutral. What was the overall charge we started with? Neutral. Okay. So as long as we didn't forget charges everywhere, we can at least compare charges. Okay. That can be helpful. You also have to have a balanced equation, which is rare in OChem. Okay. So we now go through and look at those and decide which of those generates the most stable conjugate base. So we'd start with charge. They're all negative, so that doesn't help. We'd move to an atom effect, which is size. They're all carbon, which means they're all the same. We move to an atom effect of electronegativity. They're all carbon, so there is no difference. Then I'd move to a molecular effect of resonance. Remember when I told you should be drawing lots of resonance? This is the reason why. You need to be able to look at these structures and say, yes, there is resonance, or no, there isn't. And ideally, you're doing it as quick as no resonance, yes, resonance. Seriously? Yes. Okay? If you're not there yet, that's okay. You may need to go through and make sure you've got all of your lone pair electrons drawn in. The oxygen needs to have those 2 electrons. I apologize for not drawing them on the first structure. Okay, this again kind of goes back to Unit 1. You need to be aware of implied electrons. If we looked at the red structure, I can either move the electrons here. Everybody see that? Okay. If I move them there, I would then have a double bond there. But I've got implied hydrogens. How many bonds would that carbon now have attached to it? 5. I've exceeded the octet, which in and of itself isn't a big deal. Okay. Except, is there a pi bond that I could move away from it? No. Which means, am I allowed to move the electrons there?
No.
No. Okay, I'm going to have to be smarter about drawing those arrows. Took too long to undo. Or I could move the electrons there. Okay. It's a bit small, so let me get a little bit more nitpicky with my arrow. I'm moving those electrons from that atom to that bond. Okay. Now what's the problem? I've exceeded the octet on the oxygen. Okay. If you can't see it, then you should draw it. You will see that you've exceeded the octet. So you would have to move a pi bond. There's only one pi bond to move. The ones you just made, which means no resonance. So let's just look at the one that did have resonance. Sometimes I hate life. We have 2 options again. Did you say me too? At least we're all on the same page. We now have 3 options to move those electrons. I could move them towards the hydrogen, but what happens? Exceed the octet on the hydrogen, so that doesn't work. I can move them over to this bond. It's not too far away. I have to remember the implied hydrogens. I would have exceeded the octet on that carbon. So that's not valid. Okay. The last option, I could move them here. But I would exceed the octet on that carbon. Is there a pi bond I could move?
Yes.
Yep. I'll move the electrons away from my problem. The result being everybody agree?
Yes. You mean charged?
You mean no, because that structure is neutral. And what did I start with? A negatively charged structure. The oxygen is negative. Man, I really want those other stupid drawings. The other conjugate bases that we had drawn out, we'll attempt to do those really quickly. Make sure we don't apply that. Everybody got it? So there's our three structures. Okay. One had resonance. Okay. Resonance immediately means that species is more stable, which means the hydrogen that we removed from that position was the most acidic. Okay. So when you look at a structure and see a bunch of different hydrogens, pull one off, test it. Okay. See what happens. Okay. If you literally have no clue, then you need to test every single one. Okay. In this one problem, I drew 3 answers. 2 of those answers were wrong. I would rather you are 2/3 wrong now to get 2/3 right later on the exam. Do the wrong things now. Prove to yourself that they are wrong so that you know that they are wrong. If you don't do it on your homework, what's going to happen is you will do it on the exam. Okay? It invariably happens and it sucks and I get sad. Okay? So let's avoid Mike being sad. Okay? Watch, let me push that other button again. Okay. The other thing I want to evaluate here with this resonance, because I want to pull something else. We said the resonance effect came in here, right? Where's the charge held in this resonance structure? On an oxygen. Which atom can hold the charge better? Oxygen. Why was that blue hydrogen the best one to remove? We can put a negative charge on oxygen, whereas the other 2 hydrogens, they're on carbon. We have an atom effect telling us that the blue hydrogen was better. Okay? Yes?
Does like stability of the carbon matter at all? What is like primary?
Do we encounter primary, secondary, tertiary stabilities with the anion? So what you're thinking back to is when we talked about mass spec, we talked about the stability of carbocations and carboanions. Yes, that does have an effect. Okay? It is a relatively tiny effect to the point that you probably will never see a question on it. But yes, that does have an effect on acidity. Anybody want to see an example on what he's talking about? Okay, now I'm intentionally erasing everything. Which hydrogen is the most acidic? Red, blue, or purple? Okay. This is kind of a tricky question, and this is usually why it's not asked. None of them are acidic. Okay. Those are alkane functional groups. The pKa for an alkane, which I think will show up in the next couple of slides, is 50. Okay. You're like, well, what does that mean? Water is 16. pKa, this is logarithmic, so 16 up to 50 is 35 units by powers of 10. Okay? That's not acidic. Okay? But if we're now saying which one is most acidic, we'd have to evaluate the negative charge. Okay? They would all become negatively charged positions. So we could look at atom effects, carbon. They're all carbon. Okay? We could look at electronegativity. All the same. Resonance. None of them have resonance. Induction. None of them really have induction. Hybridization. They're all the same hybridization. How could we determine it? Well, we talked about the stability of anions. And in our discussion of the stability of anions, the negatively charged, we said the primary was the most stable because there were less electrons around it. Okay? So you can go back and reference that. I don't want to spend any more time on it just because it's not a huge issue. So we would probably say that the red one was the most acidic. Okay? Not acidic, but the most acidic of the crappy choices given. Okay? And that's typically why it's not asked.
So primary is most acidic or most stable?
Most acidic because it generates the most stable conjugate base. Okay? So what we went through and did with these is we came up with these rules on explaining it, okay, based on our interpretations. Notice within those interpretations we didn't quantify anything. This is why OChem is awesome. I don't have to do fancy calculations. I don't have to deal with pKa's. Okay? I can just look at it and do some quick interpretations based off of what I know about some simple numeric arrangements, and everything is fine and dandy. That is the awesome part of OChem. Okay? The potentially less awesome part is, could we quantify each of these things? Yes, we can go back to general chemistry and use all of the knowledge you learned in Gen Chem to quantify the acidity for each of these compounds, okay, using equilibrium constants. Remember 152, the KEQ? Okay. If we take a look at this top reaction, what's happening? Okay, if I wanted to solve for the KEQ, what would I do? K equals, for those of you saying that stupid thing up there, ignore that. Really? Concentration of the, that's a good start, of the products over the concentration of the reactants. So maybe we're stumbling because I don't want to name those. I don't want to name them either, actually. So let's just say products over reactants. Okay. What is one of those products? Hydronium, aka H+. When do we see H+? Acids. So I could call this the KEQ for this reaction. But because it's producing an acid, I'm going to say, well, it's not really the KEQ. I'm going to call it the Ka because it's acting as an acid. Ka and KEQ are the same thing. There is no difference. Okay? One's just more specific. Okay? If we move to the bottom one, same deal. K is products over reactants, except what do we see as one of our products? OH minus, which is a base. So if I write out the KEQ for that one, I might call that one the KB, because it's producing a base. That's where Ka and Kb come from. Okay? Those deal with powers of 10. They look ugly and nasty and awful. This is why we switch to pKa's, because we take those powers of 10 and we drop them down to numbers usually sitting between somewhere like -7 and 50. So what you guys were taught was like 0 and 14. Okay? But your pKa's range from a much larger system than that. How could we use that to identify what's going on in here? Okay, well, I want to be able to predict which of these reactions is more valid. Okay? Because it's the same thing. I'm starting with the same thing. Okay? So I could go through and look up the pKa for these species. Okay? The pKa for a benzoic acid is something like 4.2. The pKa for hydronium is -1.5. How many people know these numbers? Just me, so I can make them up. That's fun. Because I have to make this one up. pKa for that one. Nobody really knows his number, right? Okay, just checking. Okay. So if we look at these two reactions, which one is most likely to occur? Ooh, that's dangerous.
On
These are pKa's. Well, what is the pKa referencing? Okay, the pKa is the negative log of the Ka, okay, or the K. What is your K value? Products over reactants. So if I have a K value that has a lot of products, what happens to the pKa? Well, the negative log of a large number is a small number. So the smaller the number, the more active that acid. Well, everything tries to minimize charge. If I go through here, 4.2 to negative 1.5, okay, is that a favorable reaction? No. It's going to a more active species. Okay? So that's not a favorable reaction. So if I was to draw a reaction arrow in here, I might do this. I'd say, no, that's not going to happen. Okay? How about the other one? 4.2 to negative 10.3. Same deal, that's not going to happen. But now what I'm asking is which of these is more likely? Why is the top one more likely to occur? So this one will go a half arrow, and this one will go like a little tiny little arrow. If we look, the difference between those is smaller for the top one than it is for the bottom. What does that mean? The top one is more likely to happen. I can use pKa's to quantify this. Okay? I could have also used the rules that we just evaluated. Remember we said talk about conjugate bases? I want to compare the negative species to the negative species. Which of those is more stable? Top or bottom? Top, because resonance. Which reaction is more favorable? Top. I came to the exact same freaking conclusion without dealing with any numbers. That is the beauty of OChem. We can deal with numbers, but we have to run experiments to get all those numbers. That can take days, if not weeks or months. Because OChem looks at those relationships and identifies them, we can do comparisons relatively quickly and much more quickly than we can if we went through with Gen Chem and did all the stupid calculations. And I'm calling them stupid. They're perfectly valid and awesome and fantastic, and I appreciate that someone went through and did that all, but that's not me. Right? And I'm glad it's not me. Right? I can look at those relationships and come to those same conclusions much quicker and efficiently than somebody else, right? By looking at those relationships. Right? If I wanted to quantify, I could, but we have to get all that data. Okay? So there's all the fun stuff, right? Your acid plus your base, K, Q, and all that fun, jazzy, exciting. Your Ka, whoop-de-doo, like products and concentrations, and okay. Ultimately, we come to one big conclusion. Okay? A big pKa is a weak acid. A small pKa is a strong acid. How many of you remember that? Are you just saying that because you're like, you've already talked for 45 minutes. I'm done listening to you. And yes, that was only 45 minutes. Yeah? Okay. Remember that. That's important. All right? In the upper right-hand corner, because some people started to say that when I said, what is K? Okay, this is an important equation. It shows up in your smart work. Okay? It only shows up in the smart work because it deals with numbers. I don't deal with numbers very well, so I don't ask questions about numbers, particularly ones that involve numbers doing subtractions and exponents. Like, that's just confusing. Okay? But you need that to answer one of the questions in smart work. If you want a little bit more background information on it, it's algebra. I can do it. I don't want to do it in class. Okay? So if you want to ask about it after class, by all means, we can go through and do so. Okay? So one of the things that becomes helpful is memorizing some common pKa's. Because if I knew the pKa for a carboxylic acid being 4.2, that's relatively acidic. If I compare that to the pKa of water at 15, I would know right out of the gate that the carboxylic acid should act like an acid and the water should act as a base, or rather not the acid. Okay? If I have that pK information, I can make that statement without having to do all these other comparisons. Okay? So knowing those pKa's are useful. That's why we've got this list here. That said, the only time I've memorized pKa's is because I've been doing it for 15 years. Right? I never bothered to memorize it when I went through and took OChem. I regretted that decision when I went into biochem because biochem used it a lot. So if you have to go through and move into biochemistry, having some pKa's memorized is going to be helpful. Okay? Which ones are particularly useful? Name something in biology. That's a really vague statement. Work with me here. Cholesterol. I'll work with that. Cholesterol ends in -ol. You should know alcohols. They have a pKa of 15. That becomes important because what does water have? Effectively an all. Water's pKa was 15.7. It's pretty much an alcohol at 15. Okay, so alcohols are important to know. Give me another thing in biology. What's that? Steroids are cholesterols, or the same family. Sugars are going to be your glucose carbohydrates. That's actually going to get you your alcohols again. Yeah, so let's not worry about that one. What's that?
Let's just remember alcohols.
So alcohols is a pretty big one to remember, yeah. Proteins, right? Proteins are made up of amino acids. You mean carboxylic acids? Yes. And you mean amines? Yes. Okay. Those you need to know. Okay. How many times do you see a triple bond in biochemistry or in biology? I can't remember a time I saw it. Alkenes, they do show up fairly frequently. What's their pKa though? 40. What's the pKa of water? 15. Alkenes are 3,300 times less acidic than water. Am I going to be concerned about the pKa of an alkene in biology? No. Alkanes, that shows up a lot. Those are even less acidic. Right? So those three primary categories are big. I'll circle one more that actually comes from your amino acids. The phenol functional group shows up as an amino acid side chain. That becomes important for biochemistry as well. Okay? So when we look at all of those, does any of them stand out as like, that's a little weird? Why 35 over 9? I can't even do, what is that? 4 point something? 9? 3.9? There you go. Why did I write 35 over 9? It's not 35 over 9, it's 35 and 9. Right? Because unfortunately, amines have kind of bizarre chemistry. Amines don't act as acids. They actually act as bases. Right? Why do we then list two values? Because if you look up the pKa of an amine, they'll tell you it's 9. And you'll be like, well, then it's really easy to remove a hydrogen from an amine because it's less than that of water. No, it's not. It's insanely difficult to remove a hydrogen from an amine. Its pKa is 35. Okay? The issue comes from what amines' chemistry are. R is one of the above. Amines primarily act as bases, which mean you get NH3+. Don't worry about the stereochemistry. If we removed a hydrogen, we'd have NH2 minus or NH minus. Don't worry about stereochemistry. If we're in biology, we're in a water environment, which means we're running in a pH between 0 and 14. Any pKa value outside of 14 is irrelevant. To convert the amine to the amide, removing that hydrogen, is a pKa value of 35. That is so far outside of the realm for a biology system that if you look up an amine, they're like, well, if you're looking up the pKa for an amine in a biology class, you don't care about the 35 because that's never going to happen. So we think you actually meant to look up the pKa for ammonium becoming an amine. No, jackhole, I was looking up an amine. That's what I wanted. Right? That's the confusing part with the amines. Okay? So you have to be very careful to recognize what you're evaluating. The pKa of 9 is not for an amine, it's for the ammonium. It's for the conjugate acid of an amine. Okay? Amines can oscillate all the way through there. In biology and biochemistry, you sit at the 9. In OChem, we, mess with your head and we do both. Okay? Kind of makes sense? So be careful with the amines because of that. Why do we not see that with any of the others? Because the others don't have that same issue. Okay? It's really just the amines that become problematic. Okay? So, I would highly recommend it, though I won't enforce it. You should memorize your pKa's. Your textbook talks about this thing known as the leveling effect, okay, which is kind of what we just addressed with biochemistry. Because in biology, we're looking in a water environment. I'm only really concerned about pKa's that fall between 0 and 15. Right? Which means those are the only systems that I'm going to see, protonated states between 0 and 14 on a pH scale. Okay? Because water is my solvent. But what if I move to a solvent that is not water? Well, now I can start to use other pKa's, or other pKa's become relevant. Well, in biology, we're only dealing with water. In OChem, we're dealing with any freaking solvent we want, which means all of those pKa's become relevant. So when we look at a reaction, we have to be concerned about the solvent that we're using and making sure that we aren't showing species that don't exist. The big one, which they're showing here kind of nicely, HCl. Okay. HCl will show up in a water solvent. We almost always use HCl as a water solvent, or in a water solvent. You should never show HCl in a mechanism. Why not? HCl has a pKa of -7. Okay? Which means it is so acidic that in a water environment, what happens to HCl? It dissociates, meaning it doesn't exist. So the instant you start showing HCl in a mechanism is now an invalid statement because HCl doesn't exist in that environment. What does HCl do? It reacts with the water to form hydronium. Hydronium is now the active acid in your solution. It is a relatively minor effect in mechanisms. It becomes really important in second semester, much less so this semester. Okay? But I want to address it so that you're at least aware of it now. If you take OChem 2 with me in the future, we'll see it again. Okay? And I'll try to, I like the vigorous head shaking of no. Is that what that was? Okay. We'll try to address it again in OChem 2. If you don't have to take OChem 2 at all, then don't stress about it. If you have to take OChem 2 with somebody else, they're just going to tell you to memorize your mechanisms. Okay? More than likely. Okay? This looks really familiar. I already heard some people going, oh my God, seriously? Yeah, sorta. Okay? What you learned in 152 was dealing with thermodynamics and Gibbs free energy and all of those fun things. You had RT, you had ln of K, products, reactants, all that fun stuff. Okay? And ultimately what you were doing is running calculations with those, determining something about delta G of the reaction, where they were with respect to 0, which side of the reaction was favored, reactants, products, all that fun stuff. You all remember that, right?
Sure.
Oh yeah, absolutely. Yeah, we remember it, Mike. Please don't talk about it ever again. Right? We also have your enthalpy, entropy. Oh God, yeah. All of that comes together to make this. Okay? This is what you should have learned in 152. Okay? This is what we use in OChem. It is looking at the relationship between our reactants and products, and we will then need to think about kinetics, which is the upper portion of that. Kinetics is dealing with how do we get from the reactant, thank you, our reactant, to our transition state. That's all kinetics. That's really our mechanism. How does the mechanism work? So when you guys talked about kinetics, you had to come up with mechanisms based off the rate laws and all that fun jazz, which most people have admittedly entirely blocked out. I never learned that. Yeah, you did. Okay. That's primarily where we will exist in OChem, is looking at the mechanism and evaluating that transition state. But what we're talking about is not saying what is the exact value, but what is its relative value to the reactant and to the product. Well, where is the relative value of the transition state to the reactant?
Activation energy?
It is the activation energy, yes. Where is it relative to the reactant? Come on.
Higher?
It's higher, good. Where is the relative energy of the transition state to the product?
Higher.
It's higher, good. Guess what you just learned?
Transition state.
Chemistry, good, awesome. That's what we want out of it. Okay, it's higher. How about the product? Okay. The next part of your 152 sequence was looking at the relationship between the reactant and the product. Now I don't care about the mechanism, I just care about the thermodynamics, the energy difference there. Where's the energy of the product going to be?
Ends before you go.
What do you mean depends?
It depends. Is it spontaneous reaction or not spontaneous?
When we're thinking about the energy of the product, that product energy can vary. That can be higher than the reactant or lower than the reactant, depending on our reaction. Okay? So when we go through and run our reactions, what we need to be considering is the energy of that product. Where is it relative to our reactant? If it's higher than our reactant, that reaction becomes less likely to occur. If it's less likely to occur, how can we force it to happen? We could add a catalyst. Right? Typically, they're acids and bases. Right? Or we could add energy in the form of heat. So if we encounter reactions where our product energy is higher than that of our reactants, one of the reagents that we might be adding in that would be heat. We'll probably also add an acid or a base catalyst to help force that reaction to occur. Right? Both of those cases change the dynamics of the energy diagram, facilitating that chemistry. Kind of make sense? Okay. So, relative strengths, charged and uncharged species. The stronger acidity of a positively charged, okay, now I'm confused actually. Okay. I don't know what the words are saying. Let's just look at our reaction. I just don't want to read, sorry. If we look at this reaction, okay, compare our reactants to our products. What do you think? Should our products be higher in energy or lower in energy than our reactants? Why should our products be higher in energy than the reactants? Because of the charges. Also, hydroxide, that melts my face. Hydronium, that melts my face. Water, that cleans my face. Okay? Water is now lower in energy than those. So we could use charge to help us predict this. Right? So we would predict our reactants to be relatively low energy and our products to be higher in energy. Where would I expect the transition state to be? Higher than both. Guess what? You're right. Good job. Like, really? That's all you need to do? Yes. Don't stress. Just do it. Okay. We now have an energy diagram. Could we go through and quantify all of that? Yeah, we can make it look a hell of a lot nicer. But is the gist of what is shown there also shown on the previous thing I drew? Yeah. Okay. That's where our focus needs to be. Not on getting these things perfectly correct, but recognizing the relative height of your reactants and products and drawing them. Like, well, that was too easy. It was just one step. Everything is one step. There's just another one step after it. Okay? So all you have to do after you do one step is cover the first step and move to the next step and look at just at that one. Okay? Simplify things as best you can. Okay? So if we take a look at relative acidity, if I say CH4 versus NH3, right, and I want to look at the acidities of these compounds. Okay, so my reactants, so if we went through and actually predicted this, okay, carbon we'll call blue. What would the product be if I removed a hydrogen? Okay, and then H3O plus, right? Nitrogen we'll call red. What would my product be? And? Okay, our product for blue, or sorry, our reactant for blue, relatively low energy. Well, we officially don't even know, so let's just draw it somewhere in the middle, because we could be higher or lower. Where would the product be for that one? What?
Higher.
Be higher. Okay, I agree, it should be higher. Doop. See, one step, there it is, easy. Now guess what you got to do?
Do another step?
Do another step. Okay? But this step isn't on, in addition to that one, it's going to be overlaid over the top because they aren't happening together. There's two separate reactions. The reaction is probably going to start at the same place. Why would I draw it at the same place? Neither of them are charged, so they're probably starting at about the same energy. Make sense? Okay, so we overlay it. Where should the product be for the red one? Higher in energy. Okay, I have higher being from here all the way up. If you did that and we ignored the carbon one, you'd be right. But we have the carbon one. Where is it relative to the carbon one? Should my red product be higher or lower in energy than my blue product? I don't know how to evaluate that. Charge. They're both charged. Size. They're the same size. Electronegativity. Nitrogen is more electronegative, meaning it is more stable. If it is more stable, what should its energy be relative to our blue product? Lower in energy. Why would my activation barrier for the red one be lower than it is for the blue one? The activation energy should be closest to which species, the reactant or the product, in this case? So the peak of my transition state should be closer to the reactant than it should be for the product.
It wants to make that product to be more stable.
Why should it be closer to the product? What's that?
Not enough energy it needs to make that product, so it has to be close to it.
What if your product was down here? Literally, which is closer to the peak, the reactant or the product? If it's an endothermic reaction, your transition state is going to be closer to the product because the product is higher in energy. Right? Is there a difference in energy between my two products? What does that mean about the transition state? There should be a difference there too. Okay? What if it had gone the other direction towards the product? Well, now the transition state is closest to the reactant. Will there be as much of a difference in the transition state? No, because the reactants are the same energy. Okay? This is what's known as the Hammond postulate. Okay? You don't have to freak out on knowing that, but that's officially what it's referencing. Your transition state is closest in energy to whichever state is closer to it. Okay? Which is a pretty dumb thing to say, but that's what it's saying. Reactant versus product. Okay? We will see variance within that because we aren't consistent in how we draw it, which we'll see right Now, oh, cool, no, he actually drew it nicely. What happened with our transition state for the red one? It's lower than for the blue one. Why? What's it closer to? The products. Because our product energies are significantly different, the transition state energies will be significantly different. If we flip this as an exothermic reaction, the transition state is going to be closest to our reactant. If our reactants start at the same energy, the transition states will have virtually the same energy. Okay? This becomes useful when we start to try and predict energy diagrams for individual reactions. But all we're trying to do right now is start simple, draw them on, and see what those relationships are. Kind of make sense? Okay. Ion stabilities. Okay. Which was most stable, the zero-area or the tertiary anion? Why was the zero-area more stable? So we talked about this a little bit earlier and we seemed to stumble on this. Okay. We're looking at a negative charge there. What's going to make that negative charge more stable? Being near more positive, but we don't have positive to move in organic. What do we have? Electrons. So what do I want near the negative charge? Not electrons. And if we go through and evaluate, hydrogen comes in with 1 electron. So in that first structure, there's 3 electrons around it. And the next, we'll call it 6 electrons. And the next, 9. You're right. 12 electrons. This means the zero-area anion is the most stable of these because there's less electrons around it. Right? We could do the same thing with our cations and our radicals. Well, we have to evaluate those. Those are all about evaluating charge. Well, you tell me, what did we just go through and evaluate? Charge. So are we going to be concerned about these stabilities? Yes. Okay, we need to be thinking about the stability of all of those charges all the way through. Okay. Zwitter ions are fun. For those of you in biochem, this becomes super relevant. Because when we look at that structure, or that compound, what do we have? What is that functional group? In blue. That is an amine. What is in the red? An acid. What do we have when we put those together? Hell. I mean, biochemistry. We get an amino acid. Okay? This becomes important because when we're looking at amino acids and biological systems tend to be narrowed in on very particular pHs. Okay? If we step outside of that pH, all sorts of things go haywire. Why? Well, look at the drawing that we've got. We're starting with a pH, okay, relatively low. We're probably looking at a pH of about 1. Moving up to a pH of about 7, and then we're probably up at a pH of 12. Why might biochemistry care about this? What happened to the structure?
The charge changed.
The charge changed. Well, charge isn't an important thing. Oh, wait, yeah, that's right. Yeah, it was. Okay? That dictates the intermolecular forces for my compound. That negatively charged species at a pH of 12 is going to have drastically different interactions with the environment than the positively charged species at pH 1. If I change the pH of my blood from 7.2, 4 to 7, what happens? I'm dead. And that's not a very happy thing, and that was just 0.4 pH units. Right? So our systems have tried to develop ways to maintain pHs within the bulk environment. But as we run different chemical reactions, what's going to happen? We're going to change the local pH, which changes the properties of our protein, which can allow them to bend, flip, or move. Those motions can translate into different energetics, say a muscle flexing, okay, or a neuron firing. or something telling you, ouch, this is really painful. Right? All of that goes off of subtle changes in the pH. Okay? Which means you have to be able to relate the pH to the pKa, or the acidity of each of those functional groups. And in this red box, that should look really familiar because that is the Henderson-Hasselbalch equation from 152. Yay! So what you're responsible for doing is being able to predict the protonation state for each of those functional groups. Remember how I said you needed to know the phenyl functional group? Because that's the side chain of tyrosine. You need to know the pKa for an amine because you have an amine in your amino acid. You need to know the carboxylic acid because there's an acid in an amino acid. So you have to be able to evaluate those pKa's and decide what happens at different pHs. Are you more protonated or are you more deprotonated? Okay. With that, there's usually a little cheat behind it. So let's give you the little cheat. If the pH is less than the pKa, right? Remember we said we're trying to keep in a narrow range. That's why we only evaluated the pKa's of things that were within 0 to 14. What does it mean? Well, if a pH is low, what does that mean? It's acidic. So what does that mean? I need to be in the protonated state. Okay. What if the pH is greater than the pKa? Now I need to be in the deprotonated state. Okay. This again becomes tricky with the amine functional group. Okay. The amine functional group was a pKa of 9. 9 versus 12. I'm looking at the deprotonated state. Oh, that says A minus. What's the charge on the amine? Neutral, because the protonated and deprotonated state for the amine flips from what we typically expect with most acids. Okay? Because amines act as bases, not as acids. Okay? So that trick will get you through most of the kind of questions you could encounter with Zwitter ions, which are molecules that have 2 charges. Okay? This is the last thing that I'll leave you with, just because it helps kind of summarize the relationship for being able to identify things as electron-rich or electron-poor. Really, it becomes important for a question in smart work. Okay? So when you encounter that question, this would be a good slide to pull up to help you out with it.